Hello students, very good afternoon. My name is Ranjan Kumar. This session, this week we are revising heat and thermodynamics. In yesterday's lecture we already covered thermal expansion. Today we are going to discuss about calorimetry and kinetic theory of gases. So without losing any further time, let us share our screen. So here we go. So let's start with calorimetry over here. So you must understand that when heat is added to a body, either its temperature changes or phase changes. Okay. So in calorimetry, we are going to study the about these two phenomena over here. So let's start with the discussion of temperature change. So heat added dq is related to change in temperature by this expression over here, mc dt, where dq obviously is the heat added and dt is the change in temperature, and m is nothing but the mass of substance, and c here, as you realize, c, which you can rearrange to write it as 1 by m dq by dt. So that is nothing but the heat required per unit change in temperature per unit mass of the substance, and this quantity is known as specific heat capacity of the given substance. Okay. So obviously its unit here we will be using would be, like here the unit of heat in this chapter we will be using as calorie, and the mass unit we will be using as gram, and change in temperature for example would be degree Celsius over here. So calorie per gram per degree Celsius. Okay, so if you are going to integrate this expression here both side, so net heat required in order to change the temperature from some initial value to final value over here, let's say from Ti to Tf over here. So this would be the expression, and you should realize there would be a special case. Specific heat capacity, you realize, can be a function of temperature as well. C can be regarded constant for the given temperature change. So this equation delta Q will turn out to be mc delta T over here. Okay. So one important data I want to provide you over here is specific heat capacity of water, and that is at 1 atm pressure, and that would be approximately 1 calorie per gram per degree Celsius. And this is how 1 calorie is actually defined, that is with respect to water. So you can say that 1 calorie is the heat required by 1 gram of water to change its temperature from say 14.5 degrees Celsius to 15.5 degrees Celsius at 1 atm pressure. Okay, so here the specific thing, when we are saying 14.5 to 15.5 degrees Celsius, we are trying to be accurate over here, because specific heat capacity of water will change slightly with respect to temperature, but that slight change, that change would be very very slight, and you can regard it to be constant for a change of around 100 degrees Celsius, etc. So please do understand this data is very very important. Okay. Another way of representing the same equation delta Q is equal to mc delta T is another way, is simply you can write S delta T, where S you should realize would be nothing but dq by dt simply, and also you should realize comparing this and this coefficient over here, S would be nothing but equal to mc, and this term is known as heat capacity of the given substance. So this is specific heat capacity because it is per unit mass, and this is simply heat capacity, that is heat required by a substance to change its temperature by 1 unit. Okay, and the another way of representing the same equation is delta Q. Okay, and we try to find out the water equivalent W, and that multiplied with specific heat or specific heat capacity of water, which we already see, that is equal to 1 calorie per gram per degree Celsius, and that multiplied with delta T. Water equivalent W is basically if you want to replace the material for the calculation purpose with water only. So by how much amount of water that material should be replaced, so that by adding same amount of heat, same change in temperature can be achieved. Okay, so that is water equivalent. So water equivalent, clearly you can see, like comparing this term over here and this term over here, you can see that W is nothing but M into C divided by specific heat capacity of water. Okay, so that's the idea. And apart from that, you must also understand, like here the unit of heat which we will be using in this chapter is 1 calorie, or calorie simply, or calorie is unit of heat, and when it is converted to work, okay, it will be around 4.2 joules, and this thing is known as mechanical equivalent of heat. Okay, so this is one phenomena of temperature change. Let's look at the another phenomena we were talking about, phase change. Okay, so phase change means you must understand that a substance can remain in either of the solid phase, liquid phase, or gas phase. So if heat is added to a substance, its phase may also change. So we are going to study about that. And the heat required for phase change dq is related by this expression dm into L. Okay, so dm is the mass of the substance, and L here, as you can see, L is nothing but, by the definition, simply that is dq by dm over here, that is nothing but the heat required by a substance to change the phase of its unit mass, and that quantity here is known as latent heat. Okay, and you can also rearrange that equation. Latent heat would be approximately constant, like you must realize that phase change occurs at constant temperature, so L would be a constant, so delta Q would be simply M times delta L, you can write. And two important datas I want to provide you here, so that is latent heat of fusion, okay, of ice, you can say, that is around 80 calorie per gram, and latent heat of vaporization of water is around 540 calorie per gram. And these two datas are very, very important. So, and also you should realize that all these datas which we are providing, like specific heat capacity of water, latent heat of fusion of ice, and latent heat of vaporization of water here, okay, all these datas are being provided at 1 atm pressure. Please understand, if the pressure is changed, okay, these value will also be changed. Okay, so this is the phenomena of pressure phase change over here. So let's look at one of the question which will take care of the both these things. So let's say one simple question, let's take, that is how much heat will be required to convert, say 1 gram ice at say minus 10 degrees Celsius to 1 gram steam at say 110 degrees Celsius. So this is the question over here. Apart from the data which we know already, which we have discussed already, the other data let me provide is the, like, the specific heat capacity of ice is 0.5 calorie per gram per degree Celsius, and specific heat capacity of water vapor, that would be around 0.5 calorie per gram per degree Celsius in the given temperature range. Okay, so these data will also be needed in order to solve this question. So now I'll look closely at this question. So initially what we have is 1 gram ice we are having, and that is initially at minus 10 degrees Celsius, and we have to convert it to steam at 110 degrees Celsius. So you should realize, first when we will be providing some heat, let's say delta Q1, so first thing that will happen is this ice will convert, or ice temperature will change, and its temperature will rise to 0 degrees Celsius. 0 degrees Celsius is obviously the melting point of ice at 1 atm pressure. So you should realize, like, after that, if you provide some delta Q2 heat, okay, now here it's the phase change will occur, ice will convert into water. So now we will be having, after adding delta Q2 amount of heat, we will be having water at 0 degrees Celsius. Now, if we add further some heat, let's say delta Q3, then the temperature of water will change from 0 degrees Celsius to water at 100 degrees Celsius. And then 100 degrees Celsius is nothing but the boiling point of water. So when we add more heat over here, let's say delta Q4, okay, so it will, the phase of water will change now. So now we will be having water vapor, you can say, that would be at 100 degrees Celsius. So now you add further heat. So what we will be having, let's say delta Q5. So now water vapor's temperature will rise, and let's say temperature will become, like, final temperature is 100 degrees Celsius. So like when heat is being added to 1 gram ice over here, so this is how stepwise things will occur. So we can very clearly see that where the change in temperature is occurring and where the phase change is occurring. So according to that, we will be using the expression for delta Q, that will be either equal to mc delta T or simply equal to m times L. So like for example, if we calculate delta Q1, so you can see here the phenomena of temperature change is occurring because temperature is getting changed from minus 10 degrees Celsius to 0 degrees Celsius. So formula which we will be applying would be nothing but MC, or specific heat capacity of ice here we must use, and change in temperature. So mass obviously here is 1 gram, and Ci that is given to you as 0.5, and delta T obviously you can see is nothing but 10 degrees Celsius. So you should realize that it should be nothing but 5 calorie. And similarly, if delta Q2, if we want to calculate, so here at this step you can see the phase change is happening. Okay, so the formula which we will be using is m times L, and here the fusion of ice is occurring, so m times latent heat of fusion. So m is 1, and latent heat of fusion of ice is obviously 80 calorie per gram. So this quantity will be simply 80 calorie over here. And similarly, delta Q3 would be the temperature change. So m times specific heat capacity of water into delta T. So that would be 1, and specific heat capacity of water we know is 1, and change in temperature would be 100 for this delta Q3. So that's going to be 100 calorie over here. And finally, like delta Q4 would be again m times LV. So that would be 1 into 540. So that got to be 540 calorie over here, and delta Q5 over here would be simply the uh, heat required to change the temperature of water vapor from 100 degrees Celsius to 110 degrees Celsius. So again, m specific heat capacity of water vapor into delta T. So 1 into 0.5 into delta T, that is 10. So that would be simply 5 calorie. So net heat required here, you should realize, would be the sum of all these heat exchange. Okay, so that would graphically here. Okay, let's say for example, if we intend to draw a graph of, say, temperature change, let's say in degrees Celsius versus minus 10 to 0 degrees Celsius, for example, the change in temperature of ice. So after that, temperature became constant, okay, even if we are adding heat. Okay, so 80 calorie more we added, so it becomes, say, 85. Okay, and till here there was no temperature change. This phase change occurred at constant temperature of 0 degrees Celsius. And after that, like when we again started adding heat for next 100 calorie over here, the temperature of water changed from, let's say, let's put it to not to scale, because this horizontal axis. So 100 degrees Celsius over here, temperature will reach by further adding 100 calorie of heat, so that would be 185. And please try to understand, like my diagram here is not up to scale, okay? And then again, now the phase change of water to steam will begin, okay? And this will occur at constant temperature of 100 degrees Celsius. So further 540 calorie heat we will be adding. So let's say this mark would be 725, okay? And then this would again be temperature change, okay? So the final temperature here, you should realize, is going to be 110 degrees Celsius, okay? So this is how it is happening, okay? And you should also realize, like, the slope of this slope of any line over here which represents the change in temperature, the slope of line that you can see, slope here would be nothing but that is t versus q graph. So that is nothing but dt by dq over here, and you already know this expression, like dq by dt is nothing but or dt you should write, that is nothing but mc. So obviously dt by dq, you should realize that is inversely proportional to c. So if a specific heat capacity of the material, of the substance here is greater, then the slope of t versus q graph will be smaller. Like for example, the slope of this line or this line will be double of slope of this line over here. Let's name these positions also. Let's say a, b, c, d, and EF. Okay, the slope of AB and slope of EF would be same, because specific heat capacity of ice and the specific heat capacity of water are same. So slope of AB and CD are same. But you can see the specific heat capacity of water, okay, like for example from C to D, okay, is double of specific heat capacity in the cases of AB and EF. The slope of line CD would be half that of AB, you should realize, okay? So that is one thing over here. Another thing you can understand about this situation, like for example, if in a question it is given like heat is getting supplied at some constant rate P, and you should understand like P is equal to dq by dt over here, and let's say that is constant, and you should realize rearranging dt, you can write it as dq by P. So if we want to change this scale to a temperature versus time, okay, so what we got to do, we need to divide the heat scale by this quantity P. Let's say for example, P that is given to you as 10 calorie per second over here. So T in second over here. So this time like would be for example 5 by 10. So that would be 0 0.5, and that would be 8.5, and that would be 18.5, and that would be 72.5, and finally that is 730. So 73. So it will take 73 second total in order to change the temperature, or convert ice at minus 10 degrees Celsius to steam at 110 degrees Celsius. So, and also like from A to B, how much time will it take for the temperature to change from minus 10 to 0, etc. Everything you can see on this time scale now. So it is very easy for us to convert T versus Q graph onto temperature versus time graph over here. And this gives us a very important information regarding one another thing. Let me tell you. So see, if we have an unknown substance, let's say if we have an unknown substance of mass m, okay, and let's say heat is supplied to it at a constant rate or constant power, you can say power P, and somehow we have a graph available for temperature change and phase change, let's say a temperature versus time graph is available to us. Let's say temperature is in degrees Celsius and time is in second. And this graph will more or less look similar to the previous graph we drew. So it would be something like this. Let me use some other color pen here. So it will look something like this. Something like this. So let's divide it in several zones. Let's say A, B, C, D, E, F, etc. Okay, and let's define the temperature also. That is T1, say that is T2, and that is T3, and say that is some T4. And let's put the time scale also. Let's say this time is T1, this time is T2, this time is T3, and this time is T4, T5, and T6, etc. So looking at this graph, what we can predict about this unknown substance, what we can predict. So first of all, you should realize, like obviously some part of the curve is representing the temperature change and some part of the curve is representing the phase change. So obviously the flatter part, that is BC and DE, okay, BC and DE are representing the phase change. So obviously BC is representing the phase change from solid to liquid and DE is representing from liquid to gas. Okay, so that clearly, like when the phase change is occurring from a solid to liquid over here, so T2 clearly you should realize is nothing but the freezing point of that substance. Okay, and obviously from the same logic, T3 would be nothing but, you can say, boiling point of that substance. So just by looking at these graphs, you can find out what is the freezing and boiling point of that material. Okay, and apart from that, okay, I also want to find out what would be its latent heat of fusion, what would be its latent heat of vaporization, and also we want to find out like what would be the specific heat capacity of that material in solid phase and liquid phase and gas phase, etc. So let's work one by one. So say for example, for AB, for part AB, you can clearly see like part AB must be nothing but the solid phase and this phase is liquid phase and this is about the gas phase. So from here to here, you can see that the temperature of the solid is rising from T1 to T2. Okay, so if we want to find out the specific heat capacity of the solid phase over here, solid phase, so according to the formula, that would be nothing but delta Q upon M delta T. And how will we find out this delta Q? Because the heat is supplied at constant rate P, so the amount of heat that would be supplied between time T2 and T1, that would be P times T2 minus T1 obviously, and that divided by M into the change in temperature, and the change in temperature you can clearly see is nothing but T2 minus T1. So this calculation will simply give you the specific heat capacity of solid phase over here. Okay, and now for example for BC, BC is clearly for a phase change here. So phase change is occurring and here we want to find out the latent heat of fusion of this material. So that according to definition is going to be simply delta Q upon M over here, and delta Q we have learned how to find that out. So between T3 and T2 time, so P times T3 minus T2 will be the heat added to the system, and that divided by mass will simply give you the latent heat of fusion. For similar, for using similar calculation over here for CD, you can find out the specific heat capacity of the liquid, and for DE you will be able to find out the latent heat of vaporization, and for EF you will be able to find out the specific heat capacity of the gas. Okay, or vapor phase you can say. So like I hope I have made it clear that how to calculate these things. Okay, so this was one specific type of question. Okay, another thing I want to discuss about calorimetry is one another aspect that is known as something like principle of calorimetry. Okay, and principle of calorimetry state, like for example, inside a calorimeter, which you can say is thermally insulated and closed, when two substances are mixed at different temperature, okay, heat lost by hot body will be equal to heat gained by cold body. Okay, so for a thermally insulated system, you realize heat gained will be equal to heat lost. Okay, so that's the idea. Okay, and let's solve a few questions regarding that in order to understand it better. So we will be basically looking at some mixing question. So first case, let's take, like, if we mix 10 gram ice at say 0 degrees Celsius to let's say 1 gram steam at 100 degrees Celsius. So if we mix these two substances in a calorimeter, we wish to find out that what would be the final composition of mixture. Means final composition of mixture means like how much would be ice, how much would be steam, and how much would be water, etc. left in the mixture, and what would be the equilibrium temperature. Okay, if we allow it to settle for a long time, okay, what would be the equilibrium temperature? These all things we want to find out. So how do we approach this question? So approaching this question, you should realize, like, ice is the cold body and the steam is the hot body. So ice would be gaining heat and steam would be losing heat. Okay, so for example, if we can check first of all, like how much heat would be required to melt all the ice. So the heat required to melt all the ice would be, you should realize, that would be nothing but um, 10 into latent heat of fusion of ice. So that would be 80. So 800 calorie heat is required. If we get some 800 calorie heat from somewhere, so obviously we will be able to melt all the ice. So but from where we will get that heat? So obviously the hot body will lose heat, and that is how the cold body will gain heat. So let's try to have an estimate that how much heat the steam would be losing. So this thing you can see, like if the all the steam, 1 gram steam condenses, so 1 into 540, that would be 540 calorie heat would be released. So you can see that 540 calorie heat is less than 800 calorie. And you should also realize now, like if the steam is losing heat and it has got condensed completely, and then further its phase change will occur. Okay, so the 1 gram steam which has converted to 1 gram water at 100 degrees Celsius, when its temperature decreases from 100 to 0 degrees Celsius, a further 1 into 1 into 100, 640 calorie heat would be released. So now you should, sorry, 100 calorie, total of 640 calorie heat would be released. So you should realize total of 540 plus 100 calorie heat would be released if the steam condenses and then the water temperature decreases from 100 degrees Celsius to 0 degrees Celsius. And now you should realize this total of 640 calorie heat is still less than 800 calorie heat. So the heat lost is by the steam and then by water here is not sufficient enough to melt all the ice. So like only some fraction of ice would be melted, and we wish to find out that fraction. So let's say only mi gram of ice is getting melted. So mi into 80 calorie heat would be required for this. And how much heat we are getting? So that is 540 plus 100, that is 640. So solving this clearly gives Mi is equal to 8 gram over here. So the ice which will be melting here will be equal to 8 gram only, and 2 gram remaining ice will not be able to melt. So what you can say, the final mixture will be composed of 2 gram ice that would be left, and remaining 8 gram ice which has melted, and 1 gram steam which has condensed, and altogether this will become 9 gram water. And what would be its equilibrium temperature? Equilibrium temperature theta equilibrium, you can say, will be nothing but 0 degrees Celsius. So that is one of the uh, variety of this thing. Let's look at the another variety also quickly. So second variety is, let's say if we are mixing 5 gram ice at 0 degrees Celsius plus 1 gram steam at 100 degrees Celsius. Okay, so you should realize here, like first of all, five in order to melt 5 gram ice, 400 calorie heat would be required. Okay, and in order to condense 1 gram steam, 540 calorie heat would be released over here. So 400 here and 540 calorie here, you should realize. And if so obviously the heat of condensation is more over here. So what will you can say, like the ices, like the water temperature which is at 0 degrees Celsius will try to rise. So for that 500 calorie extra heat would be required, but the heat of condensation is not that much. So you should realize that the theta equilibrium, the equilibrium temperature here would be somewhere lying between 0 to 100 degrees Celsius, and the heat exchange relationship, heat lost is equal to heat gained. So heat gained would be nothing but 400 calorie, that would be for the melting, and plus let's say the equilibrium temperature is theta, so 5 gram water, so 5 into 1, and its temperature change will be from 0 to theta, and that will be equal to heat lost. So heat lost by the steam in getting itself condensed, so that would be 1 into 540, and that condensed water will now change its temperature from 100 to theta. So the heat lost would be like 1 into 1 into 100 minus theta over here. So that is heat gained and that is heat lost, and solving that clearly, theta you will be getting it as 40 degree Celsius over here. So you should realize that theta is equal to 40 degrees Celsius would be equilibrium temperature, and final mixture will contain only of water, and that would be simply 6 gram water over here. 5 gram ice has melted and 1 gram steam has condensed, so total of 6 gram of water here. And the third situation also, let's discuss, like for example 1 gram ice is mixed with 1 gram steam here. So clearly you can see like steam is in too much excess, because 1 gram steam when it condenses, okay, it will be releasing 540 calorie of heat, and 1 gram ice will be needing only 80 calorie to melt, and further 100 calorie of heat to raise its temperature from 0 to 100 degrees Celsius. So obviously steam is in excess. Okay, so all the steam will not be condensing, so we wish to find out that how much steam would be condensing. Okay, so in order to do that, heat gained is equal to heat loss. So heat gained would be clearly 80 for melting and 100 calorie for temperature change, and that will be coming from by the condensation of the steam. So let's say mv into, let's say, 540 calorie per gram is its latent heat of vaporization. So solving the mass of the steam which has got itself condensed, we will be getting it as 1 by 3 gram only. Okay, so you should realize, so finally we will be left up with 2 by 3 gram of steam. Okay, and remaining 1 by 3 gram will be condensing into water, and there is 1 gram water also, so that would be 4 by 3 gram water, you can say, and this whole thing would be at 100 degrees Celsius, you realize. So like basically the idea here is one tip, so I want to give you, like for example, if mass of ice, you should realize mass of ice by mass of water vapor, okay, is greater than 8, you should realize, then you can say the final mixture will be some ice that would be left unmelted plus some water, and that would be at 0 degrees Celsius. And second case, if mi by mv, you can say, is greater than 3 but less than 8, then the final mixture will be only water at some equilibrium temperature theta, which would be greater than 0 degrees Celsius and less than 100 degrees Celsius, like we saw in the second case. And third, if mi by mv is less than 3, that you can say that here steam would be in excess. So the final mixture will compose of um, some water and some steam here. Okay, and the equilibrium temperature here would be nothing but 100 degrees Celsius. So this is one of the key idea here. And since the very beginning, we are saying that all these calculations, all these data which we are having is at the atmospheric pressure, that is at 1 atm over here. So what will happen at another temperature? So another pressure. Okay, so pressure temperature curve, or PT curve, simply look at. It is PT diagram, and let's have it for water here. So the PT diagram here, okay, will be something like this for water. Okay, PT diagram would be something like this for water. Okay, let me explain it for you. So let's say this point is A, this point is O, this point is B, and this point is C. So this region over here is the region of vapor, okay, or the region of gas phase. This region is of liquid, and this region of this solid. So what do we mean over here? So if we are having some pressure temperature condition, for let's say this diagram is of water, so pressure temperature condition of water is given, and let's say it lies somewhere here. So if it lies somewhere over here, its phase would be vapor. If it lies in this zone, it would be liquid, and if it lies in this zone, it would be solid, you should realize. So what will happen? What can be the case? Like for example, if it lies on this curve OA. Let's say, what is OA? So you should realize this is at the boundary between solid and vapor phase. So you should realize, like on this line OA, solid and vapor can coexist. Okay, like for example, in the previous example, we saw that at 0 degrees Celsius, at 1 atm pressure, okay, ice and water were coexisting. At 100 degrees Celsius, 1 atm pressure, vapor and liquid were coexisting. So here OA is the line where solid and vapor coexist, and that here is known as sublimation curve. Okay, that here is known as sublimation curve. Similarly, OB, this line OB, you should realize that is the boundary between solid and liquid phase. So on this line, okay, for the pressure temperature condition, solid and liquid will coexist. So this here is known as fusion curve. And similarly, OC, on this line, liquid and vapor will be coexisting. So, and that is known as vaporization curve over here. And can you see any pressure and temperature condition where all the phases will be can coexist together? So obviously, let's look at this point O over here. So this point is separating all the phases all together. So at this specific point over here, at this specific condition of temperature and pressure, the all phases of the material can coexist together. So this point O here is known as triple point. Okay, triple point of that substance. So here this graph is for water I have drawn. So this would be a triple point of waters. Again, I am repeating. So triple point is the pressure temperature condition where all the phases of the material will be coexisting together. Okay, and now another important point, this C, the C is known as critical point. Critical point. And critical point is defined as, like, for example, a substance cannot exist in liquid state at temperature greater than critical temperature. Let's have a larger scale. So if we are having material over here, okay, so if we compress, okay, if we decrease the pressure, generally even we will be decreasing the pressure, like for example here to here, okay, so pressure decreasing would be or here would be we will be able to uh, or pressure compressing we are, so from vapor to liquid we can make it on uh, releasing the pressure, it could be converted from liquid to vapor. So but beyond the critical temperature, you should realize that regardless of how high the pressure may be, vapor cannot be liquefied. So even at this point, if you are increasing the pressure, okay, beyond this critical temperature, you will not be able to liquefy it, because beyond critical temperature this material will be able to remain only in gaseous phase. So that is the critical point over here. And for water, let's have some data. Let me give you. So first of all, the triple point. So triple point of water is, let's say T, let's use in degrees Celsius, and P, let's say use in atm. So the triple point of water is 0.01 atmospheric pressure. This is the line of atmospheric pressure. This is 1 atm pressure, say. So obviously this point here, that would be on the fusion curve. So pressure, so the critical temperature is 374.14 degrees Celsius for water. Okay, and let me also give you the critical pressure here, that would be 218 atm. Okay, so these data, if you wanna remember, like, you can remember it. Okay, so this will be all about the calorimetry. And initially in the beginning of this lecture I told you that kinetic theory of gases I will also be covering. So now let's move on to the kinetic theory of gases now. Kinetic theory of gases. So kinetic theory of gases, for example, in study of kinetic theory of gases, we try to relate microscopic aspect of gas motion, okay, for example speed and or kinetic energy of gas molecules, etc., with some macroscopic parameters, for example pressure, volume, temperature, etc. So we try to relate some microscopic properties with some macroscopic properties which we can measure. Obviously pressure, volume, temperature, etc., we can measure. So when we study the kinetic theory of gases, it is very important for us to understand the assumptions of kinetic theory of gases. Okay, like under what assumption this theory will be valued over. So first thing you should realize is that all gases are made up of molecules moving randomly in all direction. Okay, so there is no preferred choice of direction. So being said that, what you can say, like the average velocity, since there is no preferred choice of direction, that will be equal to zero. Average velocity, not average speed, but average velocity of all the gas molecules, okay, will be equal to zero. And this assumption will be valid only if number of molecules inside the container is very large, let's say of the order of the of Avogadro number, you can say. So this is the first assumption. And the second assumption, let me tell you, like size of molecule is very small in comparison to you can say separation between molecules. Okay, So this is one of the assumptions. And writing is taking much time, so I will simply dictate. Okay. And the third assumption is that the molecule exert no force on each other or on the walls of container except during the collision. Okay. And see, like this assumption is very, very important, because if any of the wall is exerting, like during the collision, if it is exerting any force, okay, like for example, if any of the wall is say charged, okay, it will exert electrostatic force in a given direction. So there will be a preferred choice of direction of motion. So in that case, the first statement which we wrote, okay, that is summation of vi, so since there is a preferred choice of direction, this will not turn out to equal to 0. So that is no force of interaction, you can say no force of interaction except during the collision. You should realize I'm not writing that, anyways I am explaining that to you. And the fourth assumption, you should realize that all collision between two molecules or between molecule and a wall are perfectly elastic. Okay, that is, you can say that gas and wall of container are in thermal equilibrium. Okay, because if they will not be in thermal equilibrium during the collision, they will exchange heat to each other, exchange heat, and due to that the collision will not be perfectly elastic. After the collision, the kinetic energy of the molecule may change. Okay, so for this to happen, we need our collision to be perfectly elastic. So we want the gas to be in thermal equilibrium of the wall of the container. That can happen if we allow the gas to settle for certain time before measuring any pressure, volume, or temperature. Okay, so these were the assumption, and you should understand this. And now the next thing would be, we will be looking at calculation of RMS speed, RMS speed of the gas molecule. And obviously this calculation will be applicable for a very large number of gas molecules inside a container. Okay, you have been doing this calculation in a cubical container, and let me put it differently over here. So here I will calculate in a, say, spherical container over here, and let's say how the calculation works out. Okay, so let's say let's choose one gas molecule, let's say ith molecule whose mass is m, and say it is moving with vi velocity. Let's say it is moving with vi velocity in any random direction, you can say. Okay, and you should realize this vi, the velocity of any particle, okay, is velocity of gas molecule with respect to stationary container. Okay, that is with respect to stationary container, you should realize. Okay, so this molecule, the line of motion is this, so somewhere it is going to collide on this wall of this sphere, and let's say this is the center. So we can basically draw a normal over here, and since this is elastic collision, angle of incidence will be equal to angle of rebound, and it will not lose any kinetic energy, so it will rebound with same speed over here, and let's say this angle here is theta. So if we want to find out the magnitude of change in linear momentum for this molecule over here, this would be simply 2 times m into vi cos theta over here. And the direction of change in linear momentum, you should realize this would be the direction of delta p. You should, that would be normal, or that would be towards the center. So this is delta p over here. So if we wish to calculate the average force exerted by this molecule only on the wall, so basically average force, you can say the change in linear momentum upon the average time, okay, of the collision, you can say. So that would be simply delta p by delta t over here, delta t. So delta p already we have calculated, so that is nothing but 2 mvi cos theta. And what would be the time interval between two successive collision that we have to find out? So for that, let's say, for example, the gas molecule is colliding here. The next time the gas molecule will collide over here, and similarly it will rebound, and then it will collide over here, and so on. Okay, so the time interval between two collisions, successive collision, is the time when the gas molecule moves from, let's say, this point A to this point B. So you can clearly see, so if this radius of this sphere is r, so this path length would be nothing but 2r cos theta, and that it on this path the gas molecule is moving with this vi speed. So you can clearly say that the time taken here would be nothing but 2r cos theta upon vi over r. And that's a wonderful expression we have got, because the cos theta here would be simply cancelling, and this 2 will also get cancelled. So we will be left up with mvi square upon r over here. Okay, so we are now interested in pressure. Okay, so pressure due to the collision of all the molecules. This is the average force exerted by one molecule. So and that is along the normal also. So pressure is nothing but the perpendicular force upon area. So perpendicular force due to the collision of all the molecules, you can have the summation of this term, you can say that would be m vi square upon r, and that when you will be dividing it with the total surface area of this sphere, that would be 4 pi r square. The expression you will be getting over here is m, you can take common, and that would be nothing but 4 pi r cube, and here we will be having a summation of vi square. Okay, so now it's time for us to define the RMS speed over here. Let me define RMS speed. So VRMS, that is root mean square speed, that would be, first of all, we will square all the terms. So let's say you can say summation of vi square, and then we will take the mean of it by dividing the by it total number of gas molecules, and then we will take root of it. So root mean square. Okay, so this is the definition. So clearly you can see that this quantity over here is nothing but, that would be nothing but n times vrms square. So mn vrms square, and that is 4 pi r cube. So if we multiply and divide with 3 to this term over here, so we will be having 4 by 3 pi r cube, okay, into 3. So that would be simply 4 by 3 pi r cube would be nothing but the volume. So we will be having this relationship. P is equal to mn v rms square upon 3v, where m is the a mass of each molecule, and capital N is nothing but the number of molecules inside this container. So small m into n is nothing but the total mass of the gas inside this sphere, and that got to be equal to also, like, if small n is the number of moles, and let's say molecular weight is m, so like small m into capital M, let's write it over here. Small m into capital M will be same as small n, that is number of moles, into molecular weight, and this will be nothing but mass of gas inside container, you should realize. So both these terms are same. So nmv rms square upon 3v also you can write. So please understand this equation. And now here we can use ideal gas equation. So the left hand side would become, let's say, PV is equal to, you can say, nmv rms square upon 3 over here. So PV here is nothing but, you can write it as nRT, and n here will get cancelled. Okay, so the calculation of VRMS would be simply VRMS, you can write it as 3 RT by m root under, or alternatively you can also write it as 3 KT by small m, where K is the Boltzmann constant, and this small m here is nothing but the mass of each molecule of gas. And this can be rearranged using the ideal gas equation only. So that is 3p by rho, where P is the gas pressure, and rho is nothing but the gas density. So this here is the expression for the RMS speed of the gas. Okay, using this calculation over here, using those assumptions we discussed earlier. Okay, so this is the value of Vrms, and you should realize this Vrms is directly proportional to root T and inversely proportional to root M, etc. Okay, and one another thing I want to tell you over here, that clearly you can see, like the temperature of the gas is related to the RMS speed of the gas molecule. Okay, so speed generally we think like is a frame dependent quantity. So now the question is, does the temperature depend upon the frame of reference? The answer is no, because when we were calculating, you remember, like the VI what we took, like VI is the velocity of the gas molecule with respect to stationary container. So this speed of the gas molecule has been measured, okay, or has been used in this relationship, that is only with respect to stationary container, and that is with respect to a specific frame of reference. So you can say the temperature does not depend upon frame of reference. And being said that, let's also try to have the expression of the average speed, like what would be the V average, one thing, and the another thing which we would be looking at, like the most probable speed. So average speeds expression, and we will look more about it. Like for this instant, let's only have the expression of it, and it would be nothing but 8 RT by pi m over here, or alternatively you can also write 8 kT by pi small m, and or you can also write 8 uh, p by pi rho also. Okay, and most probable speed over here, like the speed uh, uh, the most molecule will be having over here is will be given by this expression, that would be 2 RT by m, and that will also be equal to 2 kT by small m, and that would be 2 p by rho. Okay, k here you understand is Boltzmann constant. Okay, and you should also notice one more thing here. Okay, you should also notice one more thing over here, that is Vrms, the value of Vrms you should realize is greater than the value of V average over here, and that is greater than the value of V most probable speed over here. Okay, so this part we have derived, okay, in this is spherical coordinate system, and please do remember these expressions. So right now we are running short of time, and I will not be starting any new discussion. The next I would be discussing about the Maxwell's distribution curve, and how we can use the Maxwell distribution curve to calculate the average speed and the RMS speed or the most probable speed, etc. And then later on we will be looking at the translational kinetic energy of the gas as a whole. Okay, and we will also look into something called degrees of freedom of gas molecule, and we will look at law of equipartition of energy, and we will define internal energy of gas. Okay, so but since we are running out of time in this class, I'm not going to start that thing right now. Okay, so I will be covering that in the next class, and in the next class also I will be starting heat transfer. So I will try to cover conduction in the next class, and then we will move on to the radiation, and uh, the final two lectures I have planned for the first law of thermodynamics and the discussion of heat engines, etc. So that's it for today, and thank